So we are discussing Standard 12 CBSE previous year's questions and answers. So our topics for discussion today is optical instruments and web optics. Okay, so let's resume our discussion. This is first question. State Brewster's law. The value of Brewster's angle for a transparent medium is different for light of different colors. Give the result. So for what angle of incidence this unpolarized light, this is AO is the incident unpolarized light become polarized. Okay, so this angle is called the Brewster's angle. So what is the statement? It states that the maximum polarization, what is polarization? The vibration in one plane only of a ray of light may be achieved when the ray incident on the surface of transparent medium in such a way that the refracted ray makes 90 degree with the reflected ray. So this is refracted ray, this is reflected ray, this is refracted ray. So the angle between these two is 90 degree. So this angle is called the Brewster's angle. So let's see. AO is my unpolarized light incident on the boundary between the two transparent media Mn. So Mn is the boundary which separates medium 1 and medium 2, correct? So what is the significance? If we know the angle of incidence, if we know the refractive index, we can calculate the Brewster's angle. So let's do it. So the reflected light is OC. This is reflected in the same medium, and refracted means it is transmitted to the second medium. Okay. And the refracted light is OD. This is refracted light. Now, angle CON and angle NOD, these two should be 90 degree. Okay, the angle between the reflected and refracted ray. Okay, so this angle is, if this is 90 degree, so this will be 90 minus the angle of incidence, and this is 90 minus, total angle is 90 degree, so 90 minus IB, so 90 minus R and 90 minus IB. So this total should be equal to 90 degree. So we find that the IB plus R equal to 90 degree, or the angle of refraction, okay, this angle of refraction equal to 90 minus the angle of incidence, Brewster's angle. So what is Snell's law? Snell's law states that the refractive index of the first medium into angle of incidence equal to refractive index of the second medium into angle of refraction. Correct. So here one of the medium is air, so refractive index is 1. So therefore sine, so if one of the medium mu1 is air, so refractive index is 1 equal to sine I. Second medium refractive index is mu into sine R. So mu equal to sine I by sine R. This is special condition of Snell's law where one of the medium is air. So this medium is air, so it is taken as 1, or mu equal to sine I means sine of IB, and sine R is equal to sine of 90 minus IB. So sine of 90 minus IB is cos IB. So this is mu equal to tan of IB. Since the wavelength of different colors are different, hence the refractive index also different. So mu is equal to A plus B by lambda square. This is how wavelength and refractive index is related. So if wavelength is different, then refractive index is different. So if the refractive index is different, then this IB will be different. So this is what we have to prove, correct? So this is first. So you can take the screenshot. Now question number 2. Calculate the distance of an object of height h from a concave mirror of radius of curvature 20 centimeter, so as to obtain a real image of magnification 2. Find the location of the image also. Part 2. Using mirror formula, explain why does convex mirror always produce virtual image. So this is 3 marks question. Question was asked in 2016. So we know that the radius of curvature has focal length is half of radius of curvature. So let us find out the focal length, because radius of curvature given. Magnification is 2. Height of the object is HO. Need to find out the object distance and image distance. So we know that the magnification is equal to V by U, image distance by object distance. The magnitude of image distance to object distance is magnification. So 2 is V by U. So therefore this is the relation between image and object distance. V is 2U. Image distance is twice of object distance. Now apply mirror formula. 1 by V plus 1 by U is 1 by F. Put the value of U and V in terms of U. So we find U is 15 centimeter. If U is 15, then V is 30. Correct? Thus, the object distance is 15 centimeter in front of the mirror, and the position of the image is 30 centimeter. Very easy question, just simply application of mirror formula. Now, second part, using mirror formula, explain why does a convex mirror always produce virtual image. So we know that the convex mirror focal length is positive. Hence, from the mirror formula, one by V plus 1 by U equal to 1 by F. So as it is real, so U is equal to, by coordinate convention, U is always negative. So 1 by V equal to 1 by F minus 1 by minus U. So V is equal to 1 by F, 1 by V is 1 by F plus 1 by U. Since V is greater than 0 and is always positive, V is positive, in other words, image formed by convex mirror is always behind the mirror. Hence, it will be virtual image. Correct? Now, next question. Draw the schematic ray diagram of a reflecting telescope showing how rays coming from a distant object are received at the eyepiece. Write 2 important advantages over the reflecting telescope. So we will describe now advantages of reflecting telescope. So schematic of reflecting telescope. Okay. So the rays from infinity are coming parallel. These 2 rays are coming parallel. Okay. This is the primary mirror, reflecting type. So it reflects both the rays, and by this secondary mirror it gets reflected by this, and ultimately there is a eyepiece here from which we can see the image. If we keep our eye here, then we can see the distant object. So what is the advantage of reflecting mirror? There is no chromatic aberration. Chromatic aberration means because of the lens behaves like a prism, so it splits into, it produces dispersion. Okay, so spreads of colors because of refraction is called chromatic aberration. So there is no chromatic aberration as the objective is mirror. So this objective is mirror. Resolving power of reflecting power, that is ability of the observer to two objects distinctly, is high in the reflecting telescope. What is resolving power? Suppose there is a number plate BH16, okay, and it is MH04. Okay. Now if the resolving power, this is a number plate of a car. Now if the optical instrument is having high resolving power, then from distant place you can see each letter separately. Okay, you can distinguish that this is B, this is H. If the resolving power is less, then it looks continuous, or you cannot read it. Okay, that is the significance of resolving power. So in case of this type of telescope, reflecting type telescope, its resolving power is high and chromatic aberration is less. Correct. There is no chromatic aberration because we are using mirror instead of lens. So you can take the screenshot. Next question. In Young's double slit experiment, deduce the condition for constructive and destructive interference. Okay, at a point on the screen, draw the graph showing variation of intensity in the interference pattern against position X on the screen. So what is Young's double slit experiment? Actually, this is an interference experiment. We produce two light source, coherent light source of the same wavefront, using the same wavefront by division of wavefront. Okay, so this produces two wavefronts. Single wavefront, light is coming in this form of wavefront, correct? So these two light, there are two pinholes. So in this cardboard, so there are these two pinholes acts as primary, secondary source of light. So this primary light, the incident wavefront splits into two wavefronts, and as it advances, these two wavefront interference, somewhere we get bright spot, somewhere we get dark spot. The bright spot points are called constructive interference, in phase interference, and where we get the dark fringe, it is called destructive interference, out of phase interference. So let's see. Young's double slit experiment, simplest experiment to show interference of light in Young's double slit experiment. This was the first experimental evidence to prove interference in a practical way. Okay, so delta is a narrow slit of width, and so this image in the second page. Delta is the narrow slit of width 1 millimeter. This is also very important, that the slit width should be less. Illuminated by a monochromatic source of light, means the incident light is single wavelength. Okay, at a suitable distance 10 millimeter from delta. Two slits are the light source. Okay, S1 and S2 are placed parallel to S. When screen is placed at a large distance, means where the interference is obtained, this is the screen, correct? So when the screen is placed at a large distance, about 2 meter from the slit S1 and S2, alternate dark and bright bands, okay, means constructive interference pattern appear on the screen. These are the interference bands of fringes. The band disappear when either the slit is covered. So if you cover the slit, then the band disappears. Okay, so let's see. This is the primary source of light. By division of wavefront at S1 and S2, it splits into two, correct? As it advances, interference, two wavefronts interfere with each other, so we get alternate bright and dark pattern on the screen. These are called fringes. So explanation, just see. According to Huygens principle, the monochromatic source of light illuminating the slit S sends out a spherical wavefront, correct? Since the distance is finite, the wavefront is spherical. If the distance is infinite, then it is plane wavefront. Now, the two waves of same amplitude and same frequency superimpose on each other. Dark fringes appear on the screen when the crest of one wave falls with the trough of the other, means crest of one wave falls with the trough of other. This is wave 1, this is wave 2. So out of phase interference. So automatically as per the superposition principle, the amplitude nullifies. Okay, so we get the less intensity pattern here, means destructive interference. The net displacement is y1 plus y2, correct? There we get the higher intensity, amplitude is high, so intensity will be high. We get constructive interference. So bright fringes appear on the screen when the crest of one wave coincides with the crest and crest are superimposes. Both crests are superimposes, coincide and reinforce each other. Okay, so there we get the bright fringe. So expression of fringe width. So now here, suppose D is the distance between the slit S1 and S2. This distance is D. Okay, small d. Okay. Capital D, this is the distance between the slit. This distance is between the slit and the screen. Okay. X is the distance between the central maxima O and the observation point P. So this is the observation point P. Okay. And the central maxima O. Central maxima means where the maxima happens. Okay, when the amplitude is maximum. Okay, this is X. Now, light waves is spread out from S and falls on S1 and S2. The spherical waves emanating from S1 and S2 will produce interference fringes on the screen. Okay. Now, from the geometric optics, say S1P. Now, this is S1. S1P. This is S1P. Okay. This distance. This distance. S1P square is equal to S1A square plus AP square. Pythagoras theorem. Okay. This is square plus this is square. Correct? Okay. So, from this it is D square. And this distance, D square is this. This is the base plus X minus D by 2 square. So if this distance is D, correct? So the half of the distance is D by 2. This distance is D by 2. Correct. So by calculating this, we find that S1P is this. Now, this is simply a mathematical operation that we can do. Similarly, S2P we can find out. So hence the path difference is S1P minus S2P. Path difference means this is S1P and this is S2P. So these two light sources, the distance, the difference between their path is this, correct? Path difference, we can find out the S2P is higher, S2P minus S1P. So this we can calculate, which comes out to be X into D by capital D, correct? So this is called the, now this is, now the intensity at a point P is maximum or minimum according to the path difference, is integral multiple of wavelength or an even multiple or, okay, or an odd integral multiple of half of wavelength. It depends on this. So for bright fringe constructive interference, xd by d, this is the fringe width, is equal to n lambda. So x is equal to n lambda d by small d. Okay, so nth separation is n here, what? N is equal to 0, 1, 2, like this. Since the separation between the centers of two consecutive bright fringe is called the fringe width, correct? So suppose this is bright fringe, this is again bright fringe, and this is the dark fringe, okay? So the distance between the two alternate bright fringe is fringe width, or distance between the two alternate dark fringe is also the fringe width. So this separation is called the fringe width. Fringe width is normally denoted by beta. So beta is equal to 2 consecutive, nth plus 1 minus the nth 1. So beta we find that lambda d by d, correct. For dark fringe, destructive interference resulting in a dark fringe when the path difference is odd multiple of lambda by 2. Odd number is 2n plus 1. So we find the nth is equal to 2n plus 1 lambda d by 2d. So where the value of n is equal to 0 plus minus 1, 2 like this. So the fringe width is equal to, this is the same thing. The two alternative dark fringes distance of separation is called the fringe width. So here also lambda d by d. Hence all bright and dark fringes are equal width because this is interference fringes. Okay. Now diffraction fringes are of different property. So let's take the screenshot. Intensity distribution. Now fringe obtained in Young's double slit experiment are hyperbolic in shape. The intensity of all the bright fringes is same. The curve between path difference and maximum intensity is same. Okay, so this is the graph. Next question. Compare the interference pattern observed in double slit experiment with single slit diffraction pattern. Okay, now diffraction pattern versus interference pattern. Pointing out 3 distinguishing features. Very good question. So let's see. So in one column we have kept interference fringes, in the other column we have kept diffraction fringes. Okay. So interference is due to the superposition of 2 coherent waves. Diffraction is due to the superposition of secondary waves starting from different part of the same wavelength. Okay, first condition. Now second, all bright fringes are same intensity in double slit experiment. Interference path difference of one wavelength produces the constructive interference. Okay, so in case of diffraction fringes, intensity of bright fringes decreases as on the either side of central bright fringe, hence the fringes are not of same intensity. Okay, here intensities are same, here intensities are different. Single slit diffraction pattern, a path difference of one wavelength produces a minimum since the light from the center of the slit differs by half a wavelength. This gives destructive interference, whereas say in the same condition in interference fringe pattern we get constructive interference. Okay, so you can show these two pictures, okay, to elaborate more. And third is fringes are of equal width, whereas diffraction fringes are of not equal width. Correct? So that's all. This is, take the screenshot. Next question. Plot a graph to show variation of angle of deviation as a function of angle of incidence for light passing through a prism. Derive an expression for refractive index of a prism in terms of angle of minimum deviation and angle of prism. Okay, so actually this is how, this is the angle of minimum deviation, correct, delta m. So what happens, suppose this is a prism. Okay, we are representing the by a triangle, okay, section of the prism. Now this is the incident light. So the light in absence of prism, light should go straight, but because of this there are two refraction happens, refraction at the surface AB and at this. So first type refraction happens. Then again, if you draw a perpendicular here, again refraction happens. So this is the final refracted ray from the prism. If we produce them backward, then we say that the incident light, this is incident light, this is the refracted light. So this angle, this prism has deviated the incident light. So incident light is deviated by an angle delta m. So for what angle of incidence? If we change the angle of incidence here, the angle of deviation differs. Okay. So this is angle of deviation versus angle of incidence. So for a particular angle of incident, the deviation is minimum. So we have to derive that delta m is equal to a into mu minus 1, correct? So let's see. Delta is the deviation produced by the prism, a is angle of prism, mu is refractive index of the prism, correct? So this is 5 marks question. Okay. So the principal section of the prism is represented by ABC. A is angle of prism. Now, had there been no prism, the ray would have gone to PQ straight. PQ would have PQU straight. Because of this prism, refraction happens at Q, refraction happens at R, at these two places, correct? And finally it emerges in this direction. So if we produce it back, this angle, okay, this angle is the deviation angle. So for different angle of incidence, if we plot angle of incidence along x-axis and angle of deviation along y-axis, for different angle of incidence, we calculate the angle of deviation, correct? So this is actually a practical experiment we do using a cardboard pin and a prism, very simple experiment. So angle of incidence is again changed, angle of deviation changes. Then when the angle of incidence is this, then angle of deviation is minimum. After which, if we increase the angle of incidence, the angle of deviation increases. See, this angle of deviation increases. So this particular angle of incidence produces minimum deviation, okay? So this suffers, the incident ray suffer minimum deviation. This is called angle of minimum deviation. So let's, first of all, let's remove this thing to understand this calculation. So PQN is I1 is the angle of incidence, okay? So this is angle of incidence, and this is I2 is angle of emergence, okay? AQO, this is 90 degree, a normal drawn to the incident surface, okay, 90 degree, and ARO, this is also the normal to the drawn on the finally the outer edge AC. This is also 90 degree. We have to draw the normal on the incident surface to find out angle of incidence, angle of emergence, correct? Now, in this quadrilateral AQOR, this is a quadrilateral, these two are 90 degree. So the opposite two angles, means this angle and this angle, should be 180 degree, because we know that the sum of 4 angles in a quadrilateral is 360, out of which these two are 90. So other two are 180. So this is 180. So now let's put, this is angle of the prism A plus QRO is 180 degree. So we find that A plus QRO is 180 degree, equation 1. In triangle QOR, okay, in this triangle. So this is R1 plus R2 plus this angle is equal to 180 degree, correct? So QR is equal to, if we compare equation 2 with equation number 1, what we find? Okay, this is 180 degree. So if we compare these two, that QR plus A is equal to 180 degree, QR plus R1 R2 is equal to 180 degree. So it means that R1 plus R2 is A, correct? Now TQR, this angle, this angle, okay, is equal to I1 minus R1, because total is R1. This angle is total, this angle is R1, and this is opposite angle, so this is I1. So TQR equal to I1 minus R1, TRQ, this angle, okay, this angle is how much? This is I2 minus R2, correct? This is angle of emergence, opposite angle, and this is R2. So this angle is how much? This angle is I2 minus R2, okay? So therefore delta is, this is, what is delta? Delta is the external angle of this triangle, correct? So this is the external angle. This external angle of this is a triangle basically. This angle is equal to sum of these two internal angle. This plus this is equal to this delta. Okay. So let us put delta now. So delta is I1 plus I2 minus A. Okay. This is the angle of R1 plus R2 is A. We know already. Okay. Now from this equation 4, we find that the angle of deviation delta depends on angle of incidence. Experimentally, now this is very important. If we change the pin at different positions, we can change the angle of incidence. Okay. So experimentally we find that when the deviation is minimum when I1 is equal to I2 and R1 is equal to R2. Okay. So in this condition, it produces minimum deviation. So let us put I1 equal to I2 is equal to I. So 2I minus A. So I is equal to A, and in this condition angle of deviation is minimum. So let us put delta is delta M. Delta M means minimum deviation. Okay. So A is equal to R1 plus R2, and R1 equal to R2 equal to R, correct? I1 equal to I2 equal to I. This is the condition for minimum deviation. This is experimentally found. So there we find that R is equal to A by 2, correct? So apply Snell's law. One of the medium here is air, correct? This is air, but the incident angle of incident ray incident on the refracting surface. Okay. So Snell's law reduces to mu is equal to sin A by sin R. I is A plus delta M by 2. This. Now we know that when theta is very small, theta is tending to 0, then sin theta can be written as theta. So sin A plus delta M by 2 is delta M by 2, sin A by 2 is A by 2. Okay. So let's put sin A plus delta M by 2 as A plus delta by 2, A by 2, correct? So equal to this. Now this is the formula, delta is equal to A into mu minus 1. This equation 6 gives the deviation produced by a prism. Okay. Next question. What is dispersion of light? What is its cause? Dispersion of light means, suppose we have a prism. Okay. Prism is a refracting medium. Okay. Now the spread of color, suppose this is a polychromatic light. This is the incident light, white beam of light. Okay. Now when it comes out, because we know that refractive index of the prism depends on the wavelength. This A, B are Cauchy is constant. Okay, this is not angle of prism, these are constants. Okay. Now if the wavelength is different, the refractive index of will be different. Now VG or incident light VG or contains different wavelengths. Now if the wavelengths are different, refractive index is different. If the refractive index is different, then from this formula A equal to A into mu minus 1 equal to delta. Delta will be different as refractive index is different for different color. The deviation produced by the prism will be different for different color. So there will be spread, okay, spread of color, because each of these 7 constituent color present in white light will suffer different angle of deviation here. So there will be spread. This phenomenon is called dispersion, okay, the spreading of light on emergence from a refracting medium. So let's understand this. So what is dispersion? When white light passes through a prism, it splits into its constituent colors. Red, orange, yellow, green, blue, violet. This phenomenon is called dispersion. So higher is the dispersive power, higher will be the spread. Okay. Actually this causes aberration. Okay. The splitting causes aberration. If we want to see the perfect image, the dispersion should not happen. That is why instead of this type of combination of lens taken, okay, means a combination of convex and concave lens taken. This is called achromatic combination. Just to nullify the spread because of the convex, a convex lens behaves as a prism, okay, part of prism. So just to nullify the dispersive power of this lens, we use a combination of concave and convex. This is called achromatic combination, okay, just to nullify the dispersion. Okay. So I have stated clearly that okay, higher terms we neglected because as we proceed now, the power of lambda is lambda to the power 4. So lambda is of the order of 4000 angstrom to roughly 8000 angstrom. This is the visible spectrum of visible light, okay, the wavelength spread of this, okay. So if we square it, okay, then it will be very less, so we can neglect the higher terms. So that is why a plus b by lambda square is normally taken, correct. So this I have explained why the dispersion happens, why the splitting happens, correct. Now a ray of light incident normally on one face of the right isosceles prism is totally reflected as shown. This is the right isosceles prism. Okay, right isosceles prism, this angle is 90 degree. Isosceles means two sides are same. Correct. So what happens? This is the incident ray is reflected totally. Okay, nothing comes out. It's just a reflecting medium. So what must be the minimum value of refractive index of glass? Give relevant calculations. Okay, let's understand. So this is a right isosceles. Okay, so we know that the total internal reflection is the angle of incidence must be greater than critical angle. So we know that all these things we know, because if for a certain angle of incidence, okay, the light grazes the surface. This angle of incidence is called the critical angle. Okay, so if the angle of incidence is more than critical angle, then what will happen? Instead of reflection happens. This phenomenon is called total internal reflection. This is the critical angle. So if the angle of this is suppose theta c, if we make the incident angle of incidence more than theta c, then light will not transmit to this medium. Okay, light will come back to the same medium where the incident happened. Okay, this is called total internal reflection. So this is what is explained here. So each angle, isosceles triangle, one of the angle is 90 degrees, so other two angles are 45 degree each, right? So sine 45 degree, so angle of incidence should be more than theta c. That this is the condition of total internal reflection. So sine is increasing as the angle increases. So sin I is greater than sin theta c. So sin 45 degree is greater than 1 by mu. Sin 45 is 1 by root 2 is greater than 1 by mu. So mu should be greater than root 2. Correct? Root 2 value is 1.414. So the refractive index should be greater than. So we have different glasses, prism, crown glass, okay, different types of glasses for which refractive index differs. So the refractive index of that glass should be greater than 1.414 and the minimum value is 1.4. Thus, for total internal reflection, refractive index of the prism should be greater than or equal to root 2. Next question. A concave lens of refractive index 1.5 is immersed in a medium of refractive index 1.65. What is the nature of the lens? So this concave lens becomes a convex lens. This is one more question. Okay. So if you immerse a concave lens in a medium where the refractive index of it is 1.5. So this concave lens has refractive index 1.5 and the medium of refractive index is 1.65, more than this. Then this behaves as a convex lens. That's all. Okay. So this actually refraction at a double spherical surface we study when the three mediums, okay, this is the medium 1, this is medium 2, this is medium 3. Okay. So if this two medium refractive index is more than this is a double spherical surface, concave lens is actually double spherical surface. So when the bounding medium refractive index is less than the surrounding medium, here mu1 and mu3 are same, that is refractive index of the surrounding medium, and this surrounding medium has refractive 1.65 and this the lens refractive index is 1.5, then this behaves as a convex lens. Correct? Now one more question, so no more explanation required here. Use mirror equation to show that an object placed between f and 2f of a concave mirror produces real image beyond 2f. Okay. So this is how the mass distribution happens. Okay. So we know that 1 by f is 1 by u plus, this is the concave mirror formula. As the object lies between f and 2f, now at u is equal to minus f, let us put it, the v is infinity. At u is equal to minus 2f, this v becomes minus 2f. So therefore image distance is greater than minus 2f. Since the image distance v is negative, hence the image is real. Okay. That's all. Now next question. Find an expression for intensity of transmitted light and when a Polaroid sheet is rotated between two cross Polaroids. Two cross Polaroids means there is one Polaroid, the axis of Polaroid, and the second axis of the Polaroid, these two are at 90 degree. Okay. This axis and this axis are at 90 degree. This is the axis of the Polaroid first, this is the axis of the Polaroid second. If these two axes are at 90 degree, they are mutual cross Polaroids. Okay. In which position the Polaroid sheet will be transmitted intensity to be maximum. In which position of the Polaroid sheet the transmitted intensity means finally light coming with bright light comes, intensity is higher. Okay, let's see. P1, P2 are two cross Polaroids. We'll see the figure in next page. P3 is the rotating Polaroid which makes an angle theta with the first Polaroid P1. Hence the angle between P2, P3 will be 90 minus theta. Let's see the image diagram. these are cross polarities. P1 and P2 are cross polarities. So the axis, this axis, dotted axis of P1 and this dotted axis of P2 makes an angle cross polarities. Okay. This is the P3 which is continuously rotated. So what is happening? This is the incident light coming out from the first polaroid. Now as its axis rotated, this P3, so automatically the final transmitted light from the polaroid P2 will have different intensity. So this is apply the Malus law between P1 and P3. What the law states that the I dash is equal to I0 cos square theta. Okay. So this theta is this angle. Okay. So between P1, between the polaroid P3 and P2, these two, Malus law is applied between these two. Okay. So I0 is intensity, amplitude of this. So I0 cos square theta, and between P3 and P2, if we apply P3 and P2, this is between P1 and P2. Okay. P1 P3, and this is between P3 and P2. Okay, let's apply it. So the intensity is I0 here. Intensity is I0 cos square theta into cos square 90 minus theta, because if one of the angle is theta, then other angle should be 90 minus theta. So it is, my intensity is equal to I dash cos square of angle theta. For the second polaroid, this theta is equal to 90 minus theta, and I dash is already this I0 cos square theta. So we find that the I double dash is equal to I0 by 4, correct? Sin square cos square theta, and this is cos 90 minus theta is how much? Sin theta. So this is cos theta into sin theta square, correct? Now if we put 2 here, okay, then we can put 4 here. Now 2 sin theta cos theta is sin 2 theta. So this is equal to sin 2 theta whole square by 4, correct? So this is 1 by 4 sin square 2 theta. The trigonometrical transformation, that's all. So I double dash is I0 by 4 sin square 2 theta. So therefore I double dash is maximum when sin square 2 theta is maximum. So what is the maximum of sine curve? Plus 1, correct? So sin square 2 theta is 1. So 1 means what? Sin square 2 theta equal to plus 1. At various points sin square 2 theta is 1, but as per the general value condition, but here the angle is limited to 90 degree. So this is equal to sin 90 degree, correct? So 2 theta is equal to sin square 2 theta is 1, means sin 2 theta is 1. So 2 theta is equal to sin of 2 theta equal to 1. Okay, root over 1 is 1, means sin of 90 degree, pi by 2. So 2 theta is pi by 2, so theta is pi by 4. That's all. Take the screenshot. This removing all these things so that you can take the screenshot. So this we have to prove. For brighter, for maximum intensity, this theta should be equal to pi by 4. Next question. A giant refracting telescope has an objective lens of focal length 15 meter. If an eyepiece of focal length 1.0 centimeter is used, what is the angular magnification of the telescope? Okay. Now, if the telescope is used to view the moon, what is the diameter of the image of the moon formed by the objective lens? The diameter of the moon is given 3.48 10 to the power 6 meter, and the radius of the lunar orbit is 3.8 into 10 to the power 8 meter. Very good question. Here the concept will also be clear. Okay, let's see. Now, the angular magnification, okay, is given as FO by FE. FO is focal length of the objective, FE is focal length of the eyepiece. So it is given 15 by 1 into 10 to the minus 2, this is 1500, correct? This is the angular magnification produced. Okay. Now, as per this figure, okay, second is if this first part is answered. If this telescope is used to view the moon, okay, the angular size of moon is given 3.48 into 10 to the power 6, and this is 3.8. This is 3.48 10 to the power 6, and the lunar orbit size is 3.8 into 10 to the power 8. So this is the angular size in radian. So angular size of the image is 3.48 10 to the power 6 by 3.8 into 10 to the power 8 into this 1500. 1500 is the angular magnification. So thus the diameter of the image is this into FE, correct? So this into FE is equal to the diameter, focal length of the eyepiece. So this is the value, that is, it should be 13.7 centimeter, correct? Okay. Actually it was in meter, but later converted to centimeter. That's all. Answer the following question. In double slit experiment, using light of wavelength 600 nanometer, the angular width of the fringe formed on the distance at a distance 0.1 is 0.1 degree. Okay, find the space between the two slits. Okay, light of wavelength 500 angstrom propagating in air gets partly reflected from the surface of water. How will the wavelengths and frequencies of the reflected and refracted light will be affected? Okay. So this is the mass distribution 1 plus 2. Now here lambda is given 600 nanometer. Nanometer means 10 to the power minus 9 meter. Theta is given as 0.1. So convert it into radian. Degree to radian means pi by 180. This is a multiple. If you multiply, then we get it in radian. Okay. Now we know that the angular width of the fringe is lambda by d. So lambda by theta. So let's calculate 0.34. Correct. Second, we know that when the light travels from one medium to other medium, frequency never changes. Frequency is the fundamental thing. This is asked in many times why it never changes. Okay, because when light travels from one medium to other medium, the wavelength changes because velocity changes. So velocity is actually velocity in this medium is equal to the wavelength into the frequency. Okay, if it is v2, then this is changing. Okay, velocity is different in different medium, and velocity here is v1 is equal to lambda 1 into nu. Frequency never changes. Hence, in this case, frequency is reflected. In the reflected and refracted light will remain same. Frequency never changes when light gets refracted. Okay, it is a very fundamental property. Wavelength changes. So there will be no impact on frequency. Wavelength in the refracted medium in air will remain same. Wavelength in refracted medium air will remain same, because if it is reflected, so in the same medium, so wavelength will not change. Here the wavelength, when the transmitted light, wavelength will change. However, the speed in water is less because the wavelength in water is decreasing, correct? So velocity in water is less than the velocity in air. Velocity is equal to how much? Frequency into wavelength. So wavelength is different, velocity is less, so wavelength will be less, correct? So wavelength in water will be less. That's all. Now, using Huygens construction of secondary secondary wavelets, explain how a diffraction pattern is obtained on a screen due to a narrow slit on which a monochromatic beam of light, single wavelength light, is incident normally. Part 1. Second is, so that the angular width of the first diffraction fringe is half that of the central fringe. Okay. Third, explain why maxima at theta equal to n plus half of lambda by a become weaker and weaker with the increasing n. As n increases, the maxima becomes weaker and weaker. Okay. So let's see the schematic. So in this figure, diffraction at the slit caused diffraction pattern on the screen. Okay, this is the screen. This somewhere here we'll keep the screen, correct? So screen at the point M. So this is 2M, means on the screen. Here the screen M, we get the diffraction pattern. Okay. AB is incident wavefront. This is AB. This is plane wavefront. So when the light source is at infinite distance, then we say that it is a plane wavefront. Okay, plane wavefront. Okay. So what is the property of wavefront? The rays are perpendicular to the wavefront. So AB is the incident plane wavefront. Okay. As per Huygens principle, points on the wavefront acts as secondary source of light, and these light sources are coherent in nature because they are coming from the same wavefront. Okay, by division of wavefront. Hence, we can consider P1 and P2 as secondary source of wavelets. P1, P2 are secondary source of wavelets because they are in the same wavefront. Okay. As per the requirements of phase difference, these wavelets superimpose to produce diffraction pattern on the screen. That is at the point M. Correct? Okay. Now let's see. So this is central O, D1, D2, D1 dash, D2 dash. We know that the condition of getting the first minima is A sin theta is equal to lambda. Okay. Now when theta is less, then sin theta becomes theta. So theta is lambda by A. That's all. So 2 theta is equal to 2 lambda by A. So from the figure, angular width of the first diffraction is equal to lambda by A. Correct? 2 to cancel out. So it is lambda by A. Lambda by A is the angular width. Correct? This is the angular width. Now therefore the angular width of the central fringe is equal to central fringe this. So this is lambda by A means 2 lambda by A. Okay. Third part. As the value of n increases, we are moving away from the central fringe. Okay, we are moving away from the central fringe on either side. The contribution to the diffraction pattern from the wavefront is gradually decreases. Hence, the maximum becomes fader. It becomes fed. Okay, here the intensity will be maximum, and as we go along this, the intensity reduces. It becomes weaker and weaker with the value of n. That's all. So there is a very good question. Take the screenshot of it. Everything is explained in brief because I can't devote much time here to explain each question because we have to go fast. Okay. Next question. A point object O is kept in a medium of refractive index N1 in front of a convex spherical surface of radius of curvature R, which separates the second medium of refractive index N2 from the first one. Okay. This figure is given. Draw the ray diagram. We have to draw the ray diagram showing the image formation and deduce the relationship between the object distance and image distance in terms of refractive index N1, N2 and the radius of curvature. Okay. 3 marks question. asked in 2015. Okay. When the image formed above acts as the virtual image for a concave spherical surface separating the medium N2 from N1, N2 is greater than N1. Okay. This medium is having more refractive index than this medium. Draw this ray diagram and write the similar to a relation. Okay. Hence obtain the expression for the lens maker formula. Means, okay, this is lens formula. Okay. Let's see. So this is refraction at a single spherical surface AB. So I have detailed explained. Take the screenshot because this is the refraction at single spherical surface AB. AB is the surface which separates the two medium. Okay. Now this medium N2 refractive index, this medium is N1. Okay, this is written. Ray diagram. Detailed description is given. It is self-understood. You can go through this. A ray O is incident at any point N here. So to find out the angle of refraction, we have to draw the normal. Curved surface normal means the center of curvature to this point of incidence. If you draw it, then this incident light will reflect along this. So angle between the normal and the reflected light is angle of refraction. Correct? So R. So now this is I, this is R. Okay. Now using this geometric optics, simple geometry. Now using Snell's law. Snell's law is refractive index of the medium, first medium, into angle of incidence of the first medium equal to refractive index of the second medium into angle of reflection of the second medium. Okay. Now let's put it all these values. So obtain. So this is N2 by B minus N2 by U is equal to N2 minus N1 by R. Correct. This is the lens maker formula. For relationship ADC, similarly we have, okay. So the refraction at the first spherical surface ABC of the lens. Okay. Take the screenshot. Most of these things are self-explanatory. This is simply triangle. Means if you equate the ratio of sides of equal angles are same. Prove that similar triangles and then take the ratio of sides. You can find it. Okay. So this is finally our, this is the 1 by F is N2 by N1 minus 1, 1 by R1 minus 1. This is lens maker formula. Okay. So take this. Now there is a lecture on lens maker formula. You can also go through this, how it is derived. Next question. A convex lens is placed in contact with a plane mirror. Okay. A point object at a distance 20 centimeter on the axis of this combination has its image coinciding with itself. Okay. Where the object image is coinciding with itself. What is the focal length of the lens? So 20 centimeter. We know that the image formed at the focus when it is kept at the focal plane. That's all. Okay. So it's a very simple question. The object and image coincide only when it is kept on the focal plane, correct? So if the focal plane, the focal distance is given 20 centimeter, so therefore it is asked actually what is the focal length. So it is object distance and image distance are same places the image is found, so it should be the focal length 20 centimeter. Now for a single slit width A, the first minimum of the interference pattern of a monochromatic light of wavelength lambda occurs at an angle lambda by A. At the same angle lambda by A, we get a maximum for the two narrow slits separated by a distance A. Explain. Okay. Now in a single slit, first minima occurs at a path difference between the interfering waves coming from the two halves of the wavefront is lambda by 2. It should be lambda by 2, correct? The path difference, delta, is the path difference should be lambda by 2. Correct? Now, in double slit experiment, the interfering waves coming out from the two slits produces first maxima as the path difference is lambda. Okay, that's all. Now, let's move to the next question. Draw the label diagram, ray diagram showing the formation of an final image by a compound microscope at least distance of distinction. So, go to, actually here I have shown, go to self-study.in, self-study.in. Okay, there in the optical instrument chapter, how this figure is drawn, everything is mentioned, both for simple microscope and compound microscope. So this is the objective, where this is object is PQ is written. Okay, so this objective produces image for PQ. This is the image formed P1 Q1. Okay, P1 Q1 is the image formed by the objective. Okay, now this image formed by the objective serves as object for this eyepiece. For this eyepiece, this is the object, correct? Finally, this eyepiece produces image of P1 Q1 to P2 Q2. So your eye is here, correct? So eye sees the final image P2 Q2 produced by refraction at objective and eyepiece. So final image is seen as P2 Q2 of this object PQ. This is the compound microscope ray diagram. Okay. This is what is explained. Total magnification is equal to magnification of the objective into the magnification of the eyepiece. So if total, it is given, total magnification produced by the compound microscope is 20, the magnification produced by eyepiece is 5, the microscope is focused on a certain object, the distance between the objective and eyepiece is observed as 14 centimeter. This is the tube length, okay? Object and this is the tube length, the separation between the object and eyepiece. If the least distance of distinct vision is 20 centimeter, calculate the focal length of the objective and eyepiece. Okay. So magnification produced by the eyepiece is image distance by object distance for the eyepiece. So just write it down. So object distance for the eyepiece is 4 centimeter, negative in the same direction. Apply the lens maker formula, then we find the focal length of the eyepiece is 5. The tube length is equal to, this is the image distance produced by the objective plus the object distance produced by the for the eyepiece, correct? E is what? Object distance for the eyepiece. VO is what? Image distance for the objective, okay? So it is nothing but EV plus VO. So it is given that the tube length is 14. One of this image distance is 4 already given. So you find that the image distance of the objective, okay, so it is 10 centimeter. So therefore the magnifying power of the objective is equal to this. So therefore the focal length of the objective is 2 centimeter. Okay, that's all. You can take the screenshot. So for detailed diagram, how to draw this diagram and the PDF of this optical instruments, self-study.in site will give you the PDF. Okay, there you can download it. Next question. A mobile phone lies along principal axis of a concave mirror. Show with the help of a suitable diagram the formation of its image. Explain why magnification is not uniform. Mobile phone, why it is taken? It is an extended object. That is why mobile phone is mentioned. Suppose the lower half of the concave mirror's reflecting surface is covered with an opaque material, okay, where light will not get transmitted, okay. What effect this will have on the image of the object? Explain. Let's see. Okay. So this is my mobile phone. This is how it is kept. Okay. So this will be the final image. You see the diagram. So ray diagram is explained here. So if the lower half of the mirror is covered with an opaque material, still the position and size of the image formed will remain same. However, since the reflecting surface is now halved, hence less amount of light will be reflected, hence the intensity of the image formed will be reduced. Means suppose this is the mirror, so if you covered it by black paper or something opaque, make it opaque, image will form like this, because for image formation we take two rays, one passing through the focus, other parallel to the principal axis. These two reflecting rays, wherever they will meet, their image will be formed. So image will definitely formed here, correct? For the front face, this is the front, this is for the back, this will be the for each of the point will have its image here. So you can see the mobile phone, but since this up light is getting diffused, okay, this light is not there, so therefore intensity will be less. That's all. Take this screenshot. Now, two independent monochromatic source of light cannot produce sustained interference fringe pattern. Explain. Now, in order to explain this thing, now we should know what is our limitation of eye. Our limitation of eye is if something changes 10 times per second, we cannot perceive it. Okay. Now, if these light sources are not coherent, if the light sources are from different, suppose two different bulbs, okay, two different candles or one candle, one bulb, okay, these are non-coherent example. So, if the phase vibration is of the order of 10 to the power 9 times, the light coming from this and light coming from this, they will have some initial phase plus the phase difference produced because of the path difference. As the light travels from the source of light, the path difference gets produced, okay. So net phase difference here where they meet is result of initial phase difference and the phase difference produced because of this path difference. Now had these two sources of light be different, okay, non-coherent sources, then the initial phase changes 10 to the power 9 times per second. We cannot perceive even if the changes happens 10 times per second. So how can I observe this change which is happening because of the initial phase alpha 1, alpha 2, 10 to the power 9 times per second. That is why we need coherent source of light. And how it is produced? By division of amplitude and division of wavefront. Okay, this is how we can produce the coherent sources. So I have explained in detail what happens actually. So they are having initial phase alpha 1, alpha 2, and the phase difference of this alpha 1, this from the source of light reaches at P. At P point, the phase difference is equal to 2 pi by lambda into x1. x1 is the distance traveled. Because see, if you see, when the path difference is lambda equal to the wavelength, the phase difference is 0 to 2 pi, correct? This is a complete cycle. So a path difference of lambda produces a phase difference of 2 pi. So a path difference of 1 will produce a phase difference of 2 pi by lambda. So if the path difference is x, it is a unitary method, 2 pi by lambda into x. So the first light covers a distance x1, so it will produce here the phase difference will be because of the path difference 2 pi by lambda into x1. For the second source of light, when it comes to P2, this distance is suppose x2. Then the second one will have a phase difference because of the path difference is x2. So the total phase difference is equal to, this has phase alpha 1 initial phase plus 2 pi by lambda x1. For the second wave it is alpha 2 2 pi by lambda x2. Now the net phase difference between these two, beta 2 minus beta 1, is alpha 2 minus alpha 1 in this. If these two are non-coherent, then alpha 2 minus alpha 1 changes 10 to the power 9 times per second, which you cannot pursue. 10 to the power 8 times per second it is written, okay. So 10 to the power 8, let us consider even 10 to the power 8 times per second is a huge number. You cannot perceive it, okay. Since the human eye cannot follow such quick changes, hence it is necessary that this alpha 2 should be equal to alpha 1. It means they should be coherent. From two different sources, if we produce these two slits S1, S2, then this will never happen. We cannot observe the interference pattern, okay. So no fringes can be seen. But if the sources are coherent, initial phase difference alpha 2 minus alpha 1 will be 0, alpha 1 and alpha 2 same, hence coherent sources are necessary, correct? So this is the detailed explanation, because most of the time, why I am spending too much time in explaining coherent sources requirement, you can understand later, because it's a conceptual thing. You should be clear about this, why two different sources of light, non-coherent source of light cannot produce interference pattern, correct? So let's move to next question. Okay, so this is principle of superposition, y1 plus y2. This is displacement equation of the first, this is displacement of one second, then trigonometrical transformation, and after this we get this value. So amplitude is equal to 2 alpha cos phi by 2. This is the amplitude, which is the multiplied with the circular function. So amplitude, we know that amplitude is proportional to, intensity is proportional to the amplitude square. It is 4 square cos square phi by 2, correct? Okay. So we know that the path difference lambda, same thing as explained. So intensity is 4 a square cos square phi, it is given phi. So a square is equal to k by 4. This is a constant. 4 square is constant. So k by 4. Okay. So k is equal to 4 square. So a square is equal to k by 4. So therefore intensity is equal to 4 into k by 4 into cos square pi by 2 pi by 3. This is k by 4. That's all. Now next question. So if you want to take the screenshot. Okay. Now let's move to next question. How does one demonstrate using a suitable diagram that unpolarized light when passed through a Polaroid gets polarized? Okay. So now a beam of unpolarized light is incident on a glass air interface. So using a suitable ray diagram that light reflected from the interface totally polarized. This is Brewster's law. Mu is equal to tan IB. This we already explained in the first question, where mu is the refractive index of the glass with respect to air and IB is the Brewster's angle. Okay. So this is unpolarized light, means the direction of vibrations of electric vector is happening in all possible direction. So after passing through the polarimeter, it has a single mode of vibration. Okay, remaining lights are resolved. Means suppose light was vibrating like this, component of light comes along this, only parallel to the axis of the prism light comes out through the polarimeter. Correct? This Polaroid has this function. So after transmitting, it becomes a polarized light having single direction of vibration of my electric vector. Correct? So Polaroid filter is able to produce polarized light because of the chemical composition of the filter material. The filter can be thought of as having long chain of molecules that are aligned within the filter in the same direction. The general rule is that the electromagnetic vibrations that are in the direction parallel to the alignment of the molecules are absorbed. Okay. The alignment of these molecules gives the filter a polarization axis. This polarization axis extends across the length of the filter and only allows vibrations of the electromagnetic wave that are parallel to the axis to pass through. So this direction of vibration, which is parallel to the axis of this Polaroid, will get transmitted. Any vibrations that are perpendicular to the polarization will have zero component. Suppose there is a vibration along cross, means this is the direction of vibration of the Polaroid axis, and there is a vibration here. So the component along the axis of vibration is zero, because 90 degree we do not have any component cos 90 degree, correct? So it will not get transmitted. So any direction which is cross, which is orthogonal, which is perpendicular to the axis of Polaroid, will not get transmitted. Okay, so it are blocked by the filter. Thus the Polaroid filter with its long chain molecules aligned during the fabrication of the filter. The long chain molecules are stretched across the filter all over. So you can see this theory. You can write it down. Okay. So this is Brewster's law, again already explained in the first law. Don't want to repeat. Take the screenshot. Okay. This screenshot you have already taken. Or okay. Let's move to next question. Write the relationship between angle of incidence I of a prism and angle of minimum deviation, that we already covered it. Okay. Write the necessary condition for phenomena of total internal reflection. When angle of incidence is more than the critical angle, then total internal reflection. And this already we know from standard 10 onwards, nothing special. No. A convex lens of focal length 25 cm placed coaxial in contact with a concave lens of focal length 20 cm. Okay, this is a combination. Okay, so this is a combination of lenses. Will the system be converging or diverging? Let's see. F1 is 25 cm. So power is 1 by F1. 1 by meter is diopter. Okay, so plus 4 diopter is the. So power is reciprocal of focal length. Correct. Convex lens having positive focal length, so it has positive power. Okay. Concave lens having negative focal length, so it has power is negative. Correct. So this is reciprocal of focal length, and whenever you are finding power, then you convert the focal length to meter first. Then only you will get the power. 1 by meter is diopter. Okay. So therefore the combination of the system, what is happening when two lenses are kept, a convex lens placed coaxially in contact with a concave lens. So convex and concave lens are combined, correct? Concave lens are combined. So what is the combination? What is F? Combined F was 1 by F1 plus 1 by F2. This is the focal length of the equivalent length. What is equivalent focal length? Instead of two lenses, if we want to keep a single lens, and if it can produce the same image of an object where this combination was producing, this single lens is called the equivalent lens, and the focal length of this equivalent lens is called equivalent focal length. So what is the relationship? It is, suppose F is the equivalent focal length, 1 by F. F1 is the focal length of the first lens, F2 is the focal length of the second lens. So this is 1 by F is power of the combination, P1 is the power of the first, P2 is the power of the second, correct? So this is 4, and concave lens means minus power, so it is minus 1. So combination is having negative power, means negative focal length, means divergent lens, correct? Concave lens. So combination, we need a equivalent lens is a concave lens, correct? That's all. I want to finish this chapter today. How many questions left? Let me see. In a way, diffraction, in what way diffraction from each slit related to the interference pattern in a double slit experiment? Okay, two wavelengths of This is given sodium light. Okay, 590 nanometer and 596 nanometer are used in turn to study the diffraction taking place at a single slit of aperture 2 into 10 to the power minus 4 meter. The distance between the slit and the screen is 1.5 meter. Calculate the separation between the positions of the first maxima of the diffraction pattern obtained in two cases. Okay. So condition, draw this figure first. Condition of minima is y is equal to m lambda d by d, and condition for maxima here is m into lambda d by small d, correct, in these two cases. Okay, so this is the actual double slit interference pattern, this is the diffraction pattern. Okay, so these two figure also you can draw. And regarding the second, put these values. So d sin theta is 3 lambda odd, 3 lambda 1 by 2. Since theta is very small, sin theta can be treated as theta. So ultimately put this y2 value. So the path difference is equal to difference of these two, 6.75 10 to the power minus. So nothing special on this. Take the screenshot. Next question. Draw the ray diagram showing the image formation by a compound microscope. This already explained. Distinguish between the myopia and hypermetropia. Okay. Now this is something new question. So our human eye suffers from defects. Okay. Myopia means short-sightedness. Okay. Hypermetropia means long-sightedness. Short-sightedness means you can see the shortest, means nearest object, but you cannot see the distant object. Long-sightedness means you can see the distant object, but you cannot see the nearer objects. Now, so diametrically how these defects can be corrected. So remedy of this. The first part, compound microscope, was already explained. So nothing special on this. It's a repeat question. But for defect of vision, there is a separate video where I have explained each. I'll upload it, and you can check the reason. But here, for this sake of answer to this, to write the answer, I'll explain it again here. Just take the screenshot if you require. See, this is myopia. Myopia means what happens? Short-sighted people cannot see the distant object distinctly. They cannot see the distant object, but they can see the nearer object. See what is happening? For the short-sighted distance, focal length of the eye lens decreases, the power of the eye lens increases. The focal length has decreased. Focal length has decreased means what? When we can see, when the image is formed at the retina. This is the eye lens. Okay, this circle represents the eye lens. This is the eye lens. Okay, this is retina part of it. Eye lens is held in with the help of ciliary muscles. Okay, so what is happening? The power of the eye lens increases as the focal length decreased, because power is 1 by f. Correct. So now what is happening? Because the focal length decrease, so the parallel rays from distant object is coming to meet before the retina. Correct. Here they meet. So okay, so here for eye to see the image distance is all the time same between retina and eye lens. So by applying pressure on this eye lens with the help of ciliary muscles, we apply accommodation and we keep the this image distance same. So in this case, in case of myopia, what is exactly happening? When it reaches a point F, say, the accommodation fails. Beyond this, you cannot accommodate to this image at R. The image shifts from the retina. So here it is written, as the object comes closer to the eye from the infinity image, the image shifts back, and when object comes to F, the image falls at the retina. This is called the, okay, hence F is the far point. Okay, Up to this distance you can see it distinctly for the defective eye. Now since the normal power of the eye lens has increased, hence the defect can be corrected by using auxiliary lens in front of the eye lens. So power is increased, so power to be decreased. So a negative power lens means concave lens to be used, correct? So what we will do, you can see the myopia, no? You can see the nearer objects. Up to this f you can see, but you cannot see the distant objects. So what is happening, when the distant objects rays are coming, you have to form the image of the distant object at f, then only I can see. So this auxiliary lens, this is your spectacle lens. This auxiliary lens, what it does, it forms the image of the object which is at infinity at this point f. So this divergent lens produces image of infinite objects parallel at f. This is the function of this auxiliary lens. Then if the object is at f, then you can see. So the purpose of auxiliary lens is to create the image of the distant object at f, so that it can serve as object for the eye lens, and hence it is formed at the retina. Correct? For long-sighted person, what is happening? Nearer objects they cannot see, but they can see the distant objects. So what is happening for distant object? Actually, in this case also, the focal length increased. So focal length increase means what? If the f increases, the power. If f increases, the power decreased. So to correct this vision, what we will have to do? Since the focal length increased, so the power decreased, power to be increased. So for power increasing, you should use the auxiliary lens of positive power, then only power can be increased. So convex lens to be used, number one. Second, so what is the result that if the focal length decreases, then what is happening? The rays from the infinity, come to focus behind the retina. After refraction through eye lens, the image forms behind the retina. So what is happening? You have to accommodate pressure, you have to apply accommodation on the eye lens with the help of ciliary muscles to shift the image at the retina, correct? Then only you can see the distant object. So accommodation starts from infinity. Just to see, at one point I am saying that you can see the distant object, but to see the distant object, even when the object is infinite, you have to apply the pressure on the eye lens. Okay. Now as it starts earlier, it exhausts earlier. Before reaching our near point, it exhausts. So you cannot apply more pressure on eye lens. That is why you have to use the auxiliary convex lens here, correct? So that this auxiliary convex lens, so our near point shifted, end to end test. So this convex lens, what it does, it creates an image. My near point is shifted from 25 centimeter to say some 45 centimeter. So what I will do here, so this is the object kept n, so it will create an image of this object at end dash. Now this end dash serves as object for this my eye lens, correct? So what type of lens to be used to correct hypermetropia? Positive power lens, convex lens, correct? So myopia correction is given when u is infinity, then the image is equal to minus of x. So using this formula, we can find out this. Hypermetropia correction, so for this, x and d are the least distance of distinct vision for the defective eye and the normal eye. Normal eye, it is d 25 centimeter from the, and f is the focal length of the auxiliary lens. Then for infinite objects, we have to form the image at x, so that f should be equal to minus x. So negative sign indicates that the nature of the auxiliary lens is concave for this myopia correction, and for this hypermetropia correction, this x is the distance, so this the focal length of this is equal to xd by x minus d. So the x is greater than d, so therefore f should be the positive. That's Next question. State Huygens principle. Using the principle, draw diagram to show how a plane wavefront incident at the interface of the two media gets reflected when it propagates from rarer to denser medium. Hence, verify Snell's law of refraction. Okay. So, just briefly I will explain this Huygens principle. Okay. So, Huygens principle says that every point on a given wavefront acts as fresh source of light. Suppose this is the source of light and the light advances in the form of wavefront. So every point on the wavefront acts as secondary source of light and emits secondary wavelets. Okay, these are secondary wavelets. So these points are the source of light. Okay, secondary wavelets which travel in all directions with the speed of light. The forward envelope of these secondary wavelet gives a new wavefront at any instant. So if we join it, this is Huygens constitution of secondary wavefront. So if we join all these wavelets together, so this is the position of the secondary wavefront. Okay. Now, so we have to prove using Huygens principle the laws of refraction. So suppose AB is my incident wavefront. BC is my boundary of the refracting surface which separates the two media 1 and media 2. Correct? So we know that this is the plane wavefront. Why plane wavefront? Because the source of light is at infinity. So when suppose this is source of light, okay. So as it advances, so see the radius of curvature increases. Okay, it will become less curved. So ultimately after infinite distance it becomes plane. Okay, and the properties of wavefront is this: the incident ray is perpendicular to the wavefront. So these rays are perpendicular. Any perpendicular drawn on the wavefront is incident rays. So my KB and PA are the incident rays. Okay. So if have the two median been same, suppose median 2 same, so AB advanced to CD. CD would have been the position of the wavefront after an instant of time t. Okay. But because of this reflecting surface, the light coming from G perpendicular to this wavefront is incident ray, can travel only MF. Okay, this is the distance because the speed is lower in the denser medium, so it reaches to D. Similarly from B instead of D, because now two mediums are different, instead of B to D it will travel to E. So if you join all these lights, okay, all these points together, this is the position of the refracted wavefront. So C is what? Refracted wavefront. Now to prove that C is the refracted wavefront means in the same time as it takes light to go from A to C, in the same time I am assuming that B to E has traveled. Now to show that C is my refracted wavefront, we have to show that in the same time from B to E, a light from the incident wavefront G has reached and touched the surface CE from G. So GM to MF. Okay. In the same time as it requests from B to E, as the light requests the time from B to E, at the same time light travels from B to M and M to F. If we can show that all the light sources in the incident wavefront touches this surface CE, okay, after an instant of time t, then C will be our refracted wavefront. Then as per the definition of Huygens, the angle between the incident wavefront and, okay, suppose this angle is I, this is 90 degree. Achha. So if it is 90, then this is 90 minus I, and this is also 90 degree. So this angle is say 90 minus I. I am defining in angle of incidence in terms of the wavefront. So this I, this is I, this is 90 minus I. Again this is 90 degrees. So this will be equal to I. So angle of incidence is defined as the angle between the refracting medium and the incident wavefront. This is the definition of angle of incidence in terms of wavefront. Similarly, on the same corollary, we can say that angle of refraction is the angle between the refracted wavefront and the refracting surface. Correct? This is angle of refraction. Okay? So, we have to prove that the laws of refraction holds good in case of Huygens wavefront. Now just take this and follow the lecture because it will take too much time to explain. But okay, we have kept this distance same. So ultimately we found that the Snell's law can be verified using Huygens wavefront. Okay, for entire explanation you can see my video, I will upload it. So thus the result verifies the Snell's law. And by nature of construction, the second law of refraction is what? The angle of incidence, the normal and the refracting medium lie on the same plane, that is plane of the paper. Okay. So the second law is very easy, nothing to do. So nature of construction is evident that the refracted, normal and the incident ray all exist on the same plane, that is plane of the paper. Two laws are proved. Okay. Frequency of light never changes. Same repeat question. Energy of light is given by EH now. Okay. How does, next question, how does angular separation between fringes of single slit diffraction experiment change when the distance of separation between the slit and the screen is doubled? Okay, this is the formula that you can write it here. So the separation is not the function of distance between the slit and the screen, so it would not change. That's all. Okay. Now the force for the same value of angle of incidence, the angle of refraction in three media A, B, C are 15 degree, 25 degree, 35 degree respectively. In which medium would the velocity of light be minimum? Okay. So Snell's law is this. Refractive index is sin A by sin R. This is also dependent velocity of light in vacuum to the velocity of light in the medium. Correct? Now, if you put sin I by sin R, so I is 15 degree, and as the angle increases, sin also increases. Sin of 15 is less than sin of 25, and sin of 35 is higher than sin of 25, like this. So therefore R is minimum in the medium A. Okay. So the velocity of light is minimum in the medium A. Correct? So refractive velocity of light in the medium. Okay. So if the angle of incidence, where the angle of incidence is more, R is minimum in medium A, because refractive index should be same. So if sin I is less, sin R also to be less, then only refractive index of the medium can remain same. Correct? So this angle of refraction should be less. So therefore the R is minimum where the angle of incidence is minimum. Okay? And R is maximum if sin 35 degree, so sin 35 is my numerator. So sin R should be such that it should be equal to mu. So it should be, R should be 35 something, so that the mu is constant. So this R should be higher than sin 15 degree, of course. So this is what is the answer needed. Now an object, next question, let me remove it. Sorry. Okay. Next question. An object AB is kept in front of a concave mirror shown in the figure. Complete the ray diagram. This is a very basic question. The object is kept beyond the center of curvature. Okay, just draw the ray diagram. Okay. So one ray is incident parallel to the axis, other ray is passing through the center of curvature. The ray which is passing through the center of curvature will retrace its path back. Okay, and so these two rays, this reflecting ray and this, and the ray which is parallel to the principal axis, after meeting this will go through focus. These two reflecting rays are meeting at A dash B dash. So A dash B dash is the image of AB. That's all. Now draw the level diagram of reflective type telescope. Okay, so already we have done it. Two advantages that also we have discussed. So another advantage is this cheaper than the refracting time telescope. Okay, so this is equivalent. You are given L1, L2, L3 focal length 20 cm and object is 40 cm in front of L1 as shown. So final image is formed at the focus I of L2, L3. Find the separation between L1, L2, L3. This is 40 cm and final image is 20 cm. Okay. So So for the first lens, focal length is 20 cm, U is 40. It means that PQ is kept at 2f. Okay. So hence the image P dash Q dash will be formed at 2f, that is 40 cm. Okay. So draw this diagram here. This is the image of first. Then this image serves as object for the second lens. Okay. And the image formed by the second lens will serve as object for the third lens. This is how we have to calculate. Now in double slit experiment, derive the condition constructive and destructive. This already we have shown. And this is a numerical given. The beam of light consists of 800 nanometer, 600 nanometer, used to obtain the interference fringe of double slit experiment. Screen placed at 1.4 meter away. If the two slits are separated by 0.28, everything is given. Write what is given and calculate it. Okay, so basic numerical. Take the screenshot. First part is already answered. Okay. How does unpolarized light incident by Polaroid get polarized? Describe briefly. Two polar A, B are kept crossed. This already we have answered. This is how it is getting polarized. Okay. So this already we have explained. Two convex lenses of focal length A1, A2 are used as objective lenses of two astronomical telescope. Okay. So having identical eyepieces, what is the ratio of their resolving power? Okay. Which telescope will you refer and why? This is an interesting question. Let's see. Resolving power is alpha by 1.22 lambda. Okay. So resolving power of lens L1 by resolving power of lens L2 is equal to A1 by A2. Correct. So the telescope with objective aperture, the aperture A2 should be preferred for viewing this, would give better resolution if the aperture size is more, then it will give better resolution, have a higher light gathering power. Okay, more and more light can incident power of telescope. That's all. Young double slit experiment produces interference pattern. This question reduces the expression for fringe width. X bar or X or beta, okay, is equal to lambda d by 2d, correct? Lambda d by 2d. But 2d is the separation between the two light source, okay, and d is the distance of the screen from the light source, correct? Huygens principle, verify laws of refraction, same thing. Briefly explain suitable diagram. This is a repeat question. When unpolarized light, describe briefly with the help of suitable how the transverse nature of light can be demonstrated by phenomena of polarization. See, polarization was the light phenomena which could only be explained by this transverse nature of light. Okay, so transverse nature of light through polarization. So this I can explain it. The extent of polarization depends on angle of incidence called Brewster's angle. So whenever reflected and refracted rays are perpendicular to each other, then these things happens, okay. When unpolarized light passes through this, okay, so Brewster's angle, these two should be 90 degree, correct. Okay. Draw the ray diagram to show that refraction of a ray of monochromatic light passing through glass prism. Deduce the expression for the refractive index of glass in terms of angle of prism and minimum. This already explained. Briefly, how phenomena of total internal reflection is used in fiber optics. Okay. In fiber optics, what is happening? The ray once incident, it suffered total internal reflection. Okay. Fiber optic is the transmission medium used in modern fiber optic network, correct? Data communication. So total internal reflection is used in optical fiber. Optical fiber consists of core and cladding. Refractive index of the material of the core is higher than that of cladding. When a signal in the form of light is directed into the optical fiber at an angle greater than the respective critical angle, then only internal reflection happens. So it undergoes repeated total internal reflections, okay, shown in this length of the fiber. So finally the signal comes out here. Other end, almost negligible loss of intensity. So that is why it is most obvious choice for data communication nowadays. Obtain lens maker formula, this already we have explained. This particularly lens maker formula is explained in a complete video. It requires more than 30 minutes to explain everything. So that is why I am skipping it. Just take the screenshot, follow the video. Okay. Now next, this question. A converging lens kept coaxially in contact with a diverging lens is a combination of lens. What is the focal length of the combination? Depends actually. So 1 by f, the equivalent focal length is equal to 1 by f1 plus 1 by f2. Now it depends which one is more. Then accordingly, so the power, if they are in contact, then P1 plus P2. Correct. Now if one of the lens is negative, say final focal length is f1 f2 by f2 minus f1. F means f is equal to f1 minus f1 f2 by f1 into f2 by f2 minus f1. Now if f2 is more than f1, then it is positive. If f2 is less than f1, then it is negative. That's all. Correct. This is the equivalent focal length of two lenses kept in contact. Astronomical. In astronomical telescope, what is happening? The final image is formed inverted with respect to the object. Okay, it doesn't matter. So that's why this astronomical telescope. Again, you can see the self-study.in ray diagram, how the ray diagram is drawn, how to calculate the tube length. Okay, how to calculate the magnification. There are two kinds of magnification in all the optical instruments. Simple microscope, compound microscope, astronomical telescope, terrestrial telescope. So everything is explained there. So here just take the screenshot, it's an easy thing. Young double slit experiment, two slits, the distance is given. Okay. Find the distance of the second bright fringe, simply formula based. These are given, self-explanatory, you can go through this answer. Okay. How does unpolarized light gets polarized? Passes through the Polaroid. Okay. Same question, but now this time I have answered in a detailed way, because actually the polarization happens for the electric vector. Okay. This is a detailed explanation of polarization. Okay. So an illuminated object and a screen are placed 90 cm apart. Determine the focal length and nature of lens required to produce clear image on the screen twice the size of the object. Okay. So easy question. How would the angular separation of interference fringes in double experiment happens? This is again. Only it is given that the distance between the slit and the screen is doubled. Okay. So if it is doubled, then it will become 2 beta. The fringe width becomes twice. Achha, two thin lenses, 6 diopter plus and -2 diopter are in contact. What is the focal length of the combination? So what is the power of the combination? Plus 6 diopter minus 2 diopter. This is plus 4 diopter. So power is plus 4 diopter. The focal length is equal to 1/4. But this is in meter, okay? So you have to convert it into centimeter. So multiply by 100, so it is 25 centimeter, correct? So define refractive index of transparent medium is a question. The same repeat question. Linearly polarized light. Okay. This is the formula for Malus law. Again, a Young's double slit experiment, simple numerical, very easy. You should know what is the fringe width formula. This can be explained. Okay, this already we have explained. Repeat question. Okay, this already explained. This is same question, repeat question. Define brightness angle, repeat question. Achha, this sodium lamp is passed through the two polarimeters P1, P2 kept. Okay, keeping P1 fixed, P2 rotated. This also already we have explained it. For different angle of incidence, the values are calculated. That's all. Same brightness angle and brightness law. This is a repeat question. Lens-Mocker formula we have done. So this almost completes our resolving power. Okay, resolving power is that property by which we can distinguish two letters. No? Suppose A and B is written. If resolving power is less, then you can see A, B coinciding. Okay, but if resolving power is high, then you can see A and B differently. Okay. Coherent source of light means same phase of vibration, same double slit experiment. Okay. Achha, this is simple microscope magnification produced. Achha, a figure divided into squares, each of size 1 millimeter square, is being viewed at a distance 9 centimeter through a magnifying lens. So magnifying lens is a simple microscope. It is simply a convex lens, okay, of focal length 10 centimeter held close to the eye. Draw the ray diagram. So what happens? If an object is kept between the focus and its center of this lens, okay, optical center, then the extended image is produced. Okay, so if you keep it at the focus, then image is found at infinity. So area of the square object is equal to 1 millimeter square. U is given, F is given, so you can calculate the V. 90. Magnification is final image by image distance by object distance, 90 by 9, 10. So area of the square in the virtual image equal to 10 square plus 1 mm square means is equal to 100 mm square. Okay. Area of each square in the virtual image equal to, okay, magnification is 100. So angular magnification, write what is the angular magnification? Okay. No. Okay. How is wavefront different from a ray? Ray is perpendicular to wavefront, correct? Be it a cylindrical wavefront, spherical wavefront, plane wavefront, ray is perpendicular. So it travels perpendicular to the wavefront. Wavefront are the line joining points of at a time. Suppose S is the source of light. Okay, at t time it will cover a distance c into t distance. Keep S as center, Ct as radius, and draw imaginary sphere. This surface is the position of the wavefront after an instant of time t. Okay, so this is position of this secondary source of light. Correct. So Huygens principle we have already explained. Okay. So this actually finished our optical instruments, magnifying power and details of calculation. Okay. Now next class we will study about dual nature of matter and radiation. Correct. So here photoelectric effect, Hertz and Leonard's observations, Einstein photoelectric equation, very important equation that we will discuss. Then we will discuss about matter waves, the relationship, lambda, okay, the relationship and Division-Germer experiment. That detail is not there, only conclusion is required. Okay. So in our next chapter, next class we'll do dual nature of radiation and matter. Thank you very much.